Hi, guys. So, last class, what we were talking about was really kind of taking a look at our ecological footprints and how the decisions we make in terms of what we consume in terms of natural resources and the ecosystem services that we utilize, and what do we produce in terms of wastes and pollutants, and then kind of balancing that against what the planet is able to give us and the impact that we're having on the planet. Now, one of the big things that we kind of came to the conclusion with last time is that the relationship between humans and the environment is an important one, and that the decisions we make are going to impact what happens to the planet. And never has that been more true than today as we begin to look at the growth of human populations. So, today we're going to look at population dynamics, and you may have done some of this in your social studies classes before. But today we're going to really look at kind of basics for growth and then start applying that to what the current population looks like and how many resources we currently use. All right, so let's go ahead and jump right in and get our essential questions. Number one, what are the characteristics of a population? Any population, whether it's humans or animals or plants or so on and so forth. Number two, what is the difference between exponential growth and logistic growth? These are two of the most common identified forms of growth in terms of numerical advancement. And so we'll look at both of them as good models. The other we could do is linear growth, but we'll kind of avoid that here because natural systems usually don't follow linear growth. Number three, what is the growth equation and how can we use it? Uh, we do this kind of every couple of years for the census, so for the human population, but we also take censuses of other organismal populations out in the wild as well to help us better understand how they're doing in the environment and what changes may be occurring with that population. And then lastly, number four, what is the relationship between population growth and fixed resources? Because to date, we don't have any other planet to go to live on. So what's here is what we have available to us, and population needs, as the population grows, those needs increase, and the amount of resources our planet has is fixed. All right, so let's jump right in to those characteristics of populations. There are three important characteristics of a population. These are one, geographic distribution, two, density or population density, and three, the actual growth rate. Let's go ahead and start by taking a look at geographic distribution. So, you may know this better as range. The terms are used interchangeably, but essentially what you're doing is you're describing the area inhabited by a particular population. And ranges can vary tremendously. Okay, size of a range could be a rotting apple for a worm that may live in it, to the size of the Pacific Ocean if we're dealing with a whale, for example. Okay. How many individuals within that range gets us to the next characteristic, which is population density. So, population density is the number of individuals per unit area. So, in a particular amount of space, how many individuals of a particular population live there? So, to give you some examples, plants in a desert tend to have very low population density because they are spread way apart to reduce the competition for resources, water in particular. However, you look at plants in a rainforest, like a tropical rainforest, they tend to have very high population density because there's plenty of water available for all of them, and now they're competing for sunlight. We'll talk more about this as we go ahead and continue on. In our next class, we'll look a little bit more at globalization and the consumer culture. But this is a key idea that we need to kind of follow through as we go ahead and move forward. The last one that I want to talk about, the one we're going to spend a little extra time on, is growth rate. Now, this is the final characteristic of populations, and there are three factors which affect population size. One, the number of births, two, the number of deaths, and three, the number of individuals who enter or leave the population. So, should be pretty straightforward, but as individuals are born, the population goes up. As individuals die, the population goes down. If more individuals are born than die, the population goes up. If more individuals die than are born, the population goes down. It seems pretty straightforward. The other thing we will talk about for regions and ranges in terms of ecology is immigration and emigration. You may have heard these terms. We talk a lot about it politically as well. So this is the number of people who enter or leave an area. Immigration is the movement of individuals into an area. So this causes the population to increase. Emigration is the movement of individuals out of a population, causing the population to decrease. The way I remember this is immigration, I starts with an I, in. Emigration, E, exit, means to go out. So immigration is moving in, emigration is moving out. If more individuals immigrate than emigrate, the population goes up. If more individuals emigrate than immigrate, the population goes down. And so then we can go ahead and start looking at a growth rate equation. First, we have to calculate raw growth. So we take births minus deaths plus immigration minus emigration to give us a raw growth. Now, the limitation of raw growth is that, yes, we went up by 2 individuals or 2,000 individuals. Is that a lot or is that a little? Well, you don't really know until you see that compared to the total population size. For a population of 16, 2 is a pretty good growth. Okay. If you start looking at a population of 200,000, 2 is not very statistically significant. So growth rate then is probably a more reliable measure, and it is calculated by taking the raw growth and dividing that by the total population. So let's give you an example. Using this equation, births minus deaths plus immigration minus emigration to give us raw growth. Let's say we have a population of deer, and if 2 deer are born every year and 1 dies, and 2 deer immigrate and 1 emigrates, what is the growth for the population? Well, births minus deaths, 2 minus 1, that's 1, plus immigration minus emigration, 2 minus 1. So 1 plus 1 is 2 deer. Our population is growing by 2 deer every year. Is that good or is that bad? Again, we don't know until we see the starting population. Now, if I were to tell you that the population was 16 to begin with, what's the growth rate? Well, we take 2 divided by 16. That's an eighth, so that's 0.125. The growth of this population is 12.5%. So if you want a percentage, you take the decimal, times it by 100, move it 2 places. 12.5% is the growth rate for this particular population. So what does that mean when we start looking at growth rate? Well, there are 2 basic principles of population growth. One, population size and density, how many and how tightly packed are they? And 2, how many resources are available to them? The growth of a population will continue until it becomes checked by the limitation of resources available. Okay, often you may have heard of the term carrying capacity. So as there begins to be an increasing competition for resources, not everybody's going to make it because not everybody's going to get what they need to survive. This leads to 2 basic patterns of growth that we're going to explore here: exponential and logistic. Let's go ahead and start with exponential. So exponential gives you what's known as a J-shaped curve. In exponential growth, the individuals in a population reproduce at a constant rate. Okay, constant rate, not constant number. Make sure you identify the difference between the two. And under ideal conditions with unlimited resources, population grows exponentially, infinitely. Now, immediately that should jump out at you. When does this actually happen? Ideal conditions, unlimited resources. In reality, it can't for any extended period of time because our planet is finite. It has limited resources. And the real world rarely produces ideal conditions. So you can get this for a little while in populations like bacteria or something like that. But it's not going to be something we see a lot in the wild. The human population or virus population seem to be the closest things to mirror this type of growth. The next type of growth that we want to take a look at is logistic growth. Now, with logistic growth, it's going to start out like exponential growth. It starts growing pretty quickly because there's not a lot of competition for resources. But as resources become less available, the growth of a population begins to slow down. Okay. And so this slowing period is what makes logistic growth and separates it from exponential growth. So a population's growth slows or stops when it nears what's known as carrying capacity, or the maximum amount of individuals of a population a particular environment can sustain. Okay. And you'll see in your little diagram there to the lower right that it's not just a smooth S-shaped curve, although we do call it an S-shaped curve, because there's a little bit of vibration or wiggle there at the end, because you can't say, oh no, exactly two are going to be born, exactly two are going to be die to keep it right at zero. So some years more are born and then more of them die, and other years not enough are born. And so then the following year, there's a big boom because now there are going to be more born because there weren't as many born the previous year. And so this idea of carrying capacity is the largest number of individuals that a population that can produce in a particular environment. And so that flat spot at carrying capacity, that again is not truly flat here, if it were to be perfectly flat, would be what we call zero growth. So a population with zero growth has reached its steady state. This means that the average population over time is not really going to change much. Does this mean that no individuals are born? Well, no. There are going to still be individuals born. Does this mean that no individuals die? Again, no. What this means is that the birth rate and the death rate are pretty much even. Okay, so for every individual who's born, another one dies. And so the number stays constant. And this achieves steady state when it reaches carrying capacity for the environment. Now, in humans, things are a little different than when we start talking about animal or plant populations because it's not just about consumption of raw materials for feeding ourselves or providing shelter, these types of things. And we have financial differences in terms of like monetary or economic gaps. Affluence versus poverty definitely impacts the environment as well as the population itself. Affluence has more available resources and money, has higher levels of resource consumption. We use a lot more. Because we use more, we pollute a lot more, both air and water pollution from our factories and our vehicles. To get all the materials we need to build all the things that we have, we degrade the land from mining. I think about like batteries in particular for our cell phones. That's a huge one. Right? However, on the other hand, the more money our population has, typically you get better educated about many different things, including the environment. And this helps us to develop technologies which can go ahead and help us to protect species or to save the environment. This is very different from those that are in poverty who are really just focused on survival. Okay. They're going to do what they need to do to go ahead and feed their family and keep them going and alive. And sometimes that includes degrading forests or topsoil so they can produce farms, so that they can sell off materials to help support their families. This will include depleting fish and wildlife populations, again, for food or for income. And associated with a lot of these lower SES, these poverty populations, you have poorer sanitation. And they're using the polluted water from these more affluent areas or water that they polluted because they were not as careful as maybe they should have been. They also have air pollution again from other areas, as well as air pollution they produce from outdated heating or cooking sources in terms of fires, etc. So we start looking at this and we have to start thinking about, well, what does the future really look like? What faces us in the future? What problems are we going to go ahead and have? And how are we going to solve them? And the answer in many cases turns out to be in our relationship with nature. More than almost any factor, population growth will be a leading cause of environmental problems moving forward. We are called upon to deal with this rapidly growing world population. And we need to feed those people. We need to clothe those people. And that's going to become harder and harder as the number of people gets bigger. They need a place to live. They need food to eat. They need clothes to wear. So, what's that going to look like moving forward? Well, I want to throw some numbers at you. The mean per capita annual income worldwide is $2,920. That's it. That's annual. That's for an entire year. And at the same time, you probably make more than that in your family for a year. I hope you do. But what does that mean in these other countries or other places where that's the amount of money that they make? That's it. And yet at the same time, while we've got these big economic gaps, there are about 360,000 births per day and only 151,600 deaths per day. So when you start looking at that, that's not zero growth. We are increasing the population at a pretty heavy clip. And at the same time, of those people, 1 in 7 of them are hungry. But in Western worlds like the United States, 1/3 of our food is wasted. It's just wasted. The population of the United States is using twice the renewable natural resources and services that can be regenerated within our own borders. So that means we have to take those resources from somewhere else. Now, this quote here is from David Attenborough, and he is the naturalist that does a lot of those nature shows when we go ahead and start looking at planet Earth, these types of things. Now, David Attenborough says the destruction of our environment and resources cannot be stemmed unless the growth of the world's population is stemmed and ultimately reduced. We use so much, and by continuing to grow, we're going to use so much more. And that's going to be hard on our planet in terms of the resources that it has. So we have to think about that moving forward. Okay. All right. So I have a little video here. Hopefully, that'll get you thinking about with all this new growth and where these new people are coming from, where are we going to put them? Okay.
By 2030, scientists predict there'll be 1 billion more people in the world. So where are they going to live? The greatest population expansions are expected to happen in African and Asian cities, many of which are already very overcrowded, so they can't go there. 2 researchers in the States set out to build a map of potential places to put the next billion people. First, they ruled out regions with high water stress, land covered in ice, and places with unique species that need protecting. Then, they excluded densely settled areas where there are more than 100 people per square kilometre. What they are left with are zones deemed suitable for sustainable development, some classed as highly sustainable and some as somewhat sustainable. But it isn't quite that simple. Large areas of Central Africa fit the bill, with lots of natural resources, but at the moment these areas are poorly governed and there are few jobs. Another promising swathe of land is in South America. On one hand, the warm, moist climate could support crops like rice and maize, great for feeding lots of hungry mouths. On the other hand, nearby biodiversity hotspots like the Amazon basin need protecting. There are similar conservation concerns in species-rich northern Queensland, and finding suitable land isn't the only challenge. As recent refugee crises in the Middle East demonstrate, relocating people from their homelands to new shores is not easy, politically, emotionally, or practically. Also, the habitable zones on this map span multiple countries, and it's unclear how governments would work together to encourage migration there or to house people. There are other options, like creating yet more compact cities supplied with water from yet deeper wells or desalination plants, but some argue that this would be unsustainable in the long term. What is clear is that the next billion people will need to live somewhere, and urban planners, scientists and politicians will need to work together to plan where it's going to be.
Okay, so we have to think about where those next billion people are going to go. And I want to put that into a little bit of context. In 1980, approximately 4.45 billion people lived on the earth. By the year 2000, that number had grown to 5.9 billion. Today, the world's population has grown to over a staggering 7 billion people. Each year, the world's population is expected to grow by about 85 million people. To give you kind of a sense of how much this actually is, the population in the world today in 2020, well, at the end of 2020, was growing at about 1.05% per year. As of Saturday morning, 7.85 billion people is the number that we have in the United States. Okay, 7.85 billion. And if we take that 1.05% per year, that means that we're growing at a rate of 82.425 million people per year. Now, I'm 43, and by the time you're my age, we will have added another 2 billion people to our planet if that doesn't change. 2 billion. Okay. So if you think about that, 7.85 billion plus 2 billion, you're looking at almost 10 billion people on planet Earth. Now, that's a lot of people. So it's not about adding 1 billion. Now you're looking at adding 2 billion more people. And the bigger the population, we're going to generate more pollution and more waste. We're going to put more wildlife at increased risk, while natural resources are going to be exhausted even more quickly than they are today. Using today's farming techniques, it would take a piece of land about the size of a football field to provide enough food and fiber for the average American. So think about Autzen Stadium, right? For every single person if they consumed like an American. I don't know if we have enough land for that on our planet. So we need to tie this back into our discussion of sustainability. As the world changes, so does the needs of our future. Computers and other technology make communication and distribution more efficient, but with rising populations, political conflicts, and natural capital degradation, we still have to meet the needs set out by Maslow's hierarchy. And if you think about Maslow's hierarchy, this is those basic needs down at the bottom: food, water, warmth, rest, security, safety. And security, when we say that, I'm also including food security here. Food security exists when all people at all times have physical, social, and economic access to sufficient, safe, and nutritious food, which needs land to grow it. And so this needs to be done to meet the dietary needs and food preferences for an active and healthy lifestyle. We have an issue here that we're getting to a point where the land that we're currently using isn't going to produce enough, and we have to be careful about how efficient. Remember, we said 1/3 of the food in the United States is wasted. 1/3, that's a huge amount. And so, unless we take the right environmental action, we risk seeing more species die out with potentially undreamed of consequences in terms of the health and balance of nature. And we rely on that nature. We risk flood damage to the homes in which we live and devastation to the islands and others that others know as their only homes. We will see the forward march of deserts, compelling populations to be on the move, and the growing shortage of water, creating new conflicts and exacerbating old rivalries. It's a pretty bleak picture if we don't change the current habits that we have in terms of increasing population and increasing consumption. So ultimately, the air we breathe, the water we drink, the food we eat, and the energy which powers our enterprises are all threatened if we do not practice proper stewardship of the planet. And it's not going to be the governments that make these big sweeping changes, they're just your representatives. each and every one of you are going to have to make a change yourself and then convince others around you to make those changes because that's what's actually going to make a difference in the future. I'm going to leave you today with a quote from the Lorax. Unless someone like you cares a whole awful lot, nothing is going to get better. It's not. You guys are the future. The decisions you make will determine what the future for humanity and the planet is going to look like. You have it in you. Make the change. Stay healthy, stay safe. I'll talk to you guys soon. Take care of yourselves. Bye bye.